basically these are all going to be word problems. A bunch of word problems, real life types of examples. Now, I say real life types of examples. Many of these things you wouldn't necessarily do. But again, these are exercises that we can eventually apply to things that are more difficult. So we'll start off easy. Now, in your book, I just screenshotted this from page 114. It's kind of a layout of, it's not a have to, but it's a good sort of recipe to follow every time you do problems like these. So you have to choose a variable, and whatever you choose is fine. It doesn't matter. If you draw a picture and you just label it, then you don't have to really state what your variable is, because we can tell from the picture. And in most of these problems, there will be a picture, but sometimes there will not be a picture. And sometimes a picture doesn't make sense either. In a case like that, just write a variable line. So x equals, the length, even though there'll be a picture for something like that. Or x equals the number, or x equals the number of apples, or whatever, okay? You should state your variables if there is no picture, all right? You're going to write an equation. You're going to usually end up with two equations, and you're going to isolate whichever variable you're trying to maximize or minimize. You're going to rewrite rewrite so that we're going to take this primary equation, and you're going to probably have a second equation that you're going to insert that rearranged equation into. You got to find the domain, because we have to know what possible numbers are eligible for the problem. Okay, you'll take the derivative, find the critical numbers, make a number line, try to figure out where your max and mins are, watching your endpoints. It's important, and maybe add that here, include your endpoints when necessary. Okay, sometimes they're not necessary based on what the domain is, or based on what your signs are, and we'll talk about that as we go through a couple examples. But there will be endpoints for most of these problems. Okay? Questions so far? You guys have done this before, right? Okay. All right. Here's the first one. We're going to go through two examples. This is on page 115. I remember to write the pages down, so you can screenshot it there. And I'll give you the option. Do you want to go through it together, or do you want to try? How many vote for do it together? Raise your hand. Okay. Majority wins. We'll do it together. I think for this first one, it's probably a good idea. That way, because it'll jog your memory a little bit. Maybe think about this, how to kind of proceed. The best thing I can tell you is when you get to a word problem, try to use all the information. Okay, and try to write as many equations as you think you can from the information that's there, and then, of course, try to put it together. This problem is kind. They gave us a picture, in case you're bad at drawing pictures of boxes. All right. The box with no lid is going to be made from 48 square centimeters. So that's telling you area. So this has this flat piece of, do we know what it's being made out of? We don't know what it's being made out of. Material, yes. We'll call it cardboard, because boxes always seem to be made out of some form of cardboard. So we've got this sheet, 48 square centimeter sheet, that's going to be turned into a box. They tell us the base must be a square, and so we want to find the dimensions that will produce the maximum volume. All right? That makes sense, because if we're have a box, we're going to be either carrying a bunch of stuff in it, or we're going to be sending it to someone or giving it to someone. So in an ideal world, we want to have the box that can contain the most stuff, and so we're maximizing the volume. Okay. Now, I went ahead and labeled my box with X's and Y's. You can label them with whatever you want. If you want lengths and widths and heights, you can do that. Why did I make both of these X, since it's a box? Because it's a square, exactly. That's important. The base is a square, so therefore the length and the width of the base are actually the same. So we have two pieces of information in this problem. One, of course, we're trying to maximize the volume, so we're going to have a volume equation. And two, we're going to have a surface area equation, or an area equation that involves this 48 square centimeters. And then eventually we're going to put it together. So let's start with the volume. The volume's easy enough. Okay. How do you find the volume of any prism? Area of the base times the height. In this case, since it's a box, length times width times height. But just in general, whether it's a cylinder, whether it's a triangular prism, whether it's a square prism, that's what this is. This is a square prism or a rectangular prism. You're going to take the area of the base, or your base could be anything. I mean, it could be a hexagon for that matter. You're going to take the area of the base and you're going to multiply it by the height. The way I like to think about volume is I have a thin layer, like think of a ream of paper, right? Each layer sort of represents the base, and as you pile them up, then you get thickness to it. Even though technically, I mean, paper absolutely has thickness. It's microscopic, but it has thickness. But that's the way I like to think of volume. So if you take one of these and then you just kind of multiply it by however many there are, then that's where that solid comes from. Anyway, all right, so your volume for this particular problem is going to be x squared times y, because the area of the base is a square, and that's, so we call it x squared. All right, next thing we need to do is come up with the surface area, because the thing that's nice about this box is it has no top, no lid. So I have 1, 2, 3, 4, 5 sides that are being used to create this box. If it would have had a top, there'd be a 6th side. But essentially what you want to think of in your head is taking the box from flat, okay? And you're gonna picture, if you need to picture this, what we've got here is, let's see if I can draw a square. That's pretty good. We basically have a flat, oh, that was terrible. I was doing so good, right? So we have basically a flat piece of cardboard that looks like this, envisioning that this is a square and these are the sides, and we're just folding them up, right? And they tell us that the area of this whole thing is 48 square centimeters. So if you need to draw things like this out in order to come up with that area sort of formula for this, then great. Maybe you don't. Fortunately, we have the base is x squared. We've already talked about that. What is the area of one of these faces? Yx or xy. What about this one? How about this one over here? Yeah, they're all xy, right? That's the thing. That's nice when the base is a square. So we've got x squared plus how many xy's? 4. Okay. So here's my surface area, and they tell us that it also equals 48. Okay. Now, here's where sometimes it can get confusing. Which equation do I need to isolate a variable in it, and which equation do I need to insert in, right? Because at some point I'm going to take these two equations and combine them together, right? So first off, we can answer this first question with no regard to which equation we're going to use. Which variable should we get by itself? We don't need to even be concerned with which equation we're going to use. You should be able to tell me which variable you should get by itself without paying either attention, whether it's volume or surface area. X or Y? X or Y? You want to go X? You want to go Y?
Don't you need both though, or are you just saying?
We're going to isolate one of them. We got to isolate one of them because then we're gonna substitute into the other. You say Y. Why? Why do we say Y? Why do you say X? Did you say X just because it's first in the alphabet? Okay. Why do you say Y? Because what? Say again? I don't want to take the square root either, right? Because if I end up having to get X by itself, either here or here, and this one gets hairier, then you're going to eventually have to take the square root. Because I have just a sort of plain y in both, your choice should be to get y by itself. Okay, now the question is, which one are we getting by itself? Are we getting the y by itself in the surface area and then inserting that into volume? Or are we going to get the y by itself over here and inserting it into surface area? Well, which one are we trying to maximize? The volume or the surface area? The volume, we already know the surface area. Okay, so we should get this y by itself, because then we'll insert into volume and then we'll work our way through the volume. Okay, when you're trying to minimize or maximize whichever quantity you're trying to minimize or maximize, that's the one that we're eventually going to take the derivative of. Okay. The other thing that sort of is the giveaway is they give us one of the numbers. All right, so I'll be able to isolate this without having an extra variable. Okay. Solve for y and substitute into the volume equation. So we'll have to move the x squared over, and then we'll have to divide by 4x. And there we go. Okay. That is y. So then we're going to insert this into the volume equation. Like so. And then we'll simplify, and as far as we can, just to make finding the derivative easier. Okay. So let's see, what did I do first? Oh, I did it all at once. Okay. So this, you can think of this as 48 over 4x, which is 12 over x. And then over here it is minus x over 4. And then I also have to multiply it by x squared. So 12 over x times x squared is just 12x. Over here, let's see, I'm going to have an x cubed, it looks like, over 4. Or 1/4 x cubed. Just algebra. Questions so far? Yeah, so if you wanted to simplify this first and then distribute, that's fine. And how, obviously, again, the algebra in between here and here, we should be fine with, okay? So what do I do now? Now that I've simplified this as best as I can, what should I do? Find the derivative, absolutely. Find the derivative of the volume. So go ahead and do that. Actually, not yet. Sorry. Yeah, we need the domain first. Because in order to look at what our endpoints are going to be, we need to know what the domain is. Okay, so yeah, we jumped ahead. Sorry. Is it easy to find the domain as the volume sits right now? And could you do it? What might be easier? So setting the domain. Okay, obviously one of the things that is true is there's not going to be, x can't be negative. It's a measurement. Okay, so it's got to be 0 or greater. And of course, if it was 0, that would mean there would be no base. So it's going to have to be bigger than 0. The trick here, to me, what I would do is factor. And at minimum, get an x out. Maybe take a 1/4 x out, or let's take a 1/4 x out, because that fraction is messy, right? So if I take a 1/4 x out, basically dividing 12 by 1/4, what does that give you? 12 divided by 1/4, 48, correct. So we're here. Okay, if I take a 1/4 x out, now finding the domain got a lot easier. Okay, of course, we have to be bigger than 0. We can't be equal to 0. We certainly can't be less than 0. What is the highest value that x can be and still keep the volume positive? Because there's going to be a point where this thing can turn negative. What would have to happen here for this to be negative? Right, this would have to be more than 48. Okay, so x would then be, what's the highest value that x could be? Square root of 48. Okay, now again we have the same thing. If this was the square root of 48 and you square it, obviously that's 48, and this is all 0, and we have a problem. We can't have a volume of 0. Okay, so I can go up to almost equal to, but not quite, the square root of 48. So that's where I have to be greater than 0. I have to be less than the square root of 48. There's your thing. Okay, notice they're both less than, because the or equal to makes the volume 0. This is important because those essentially are our endpoints. Now, granted, they aren't actually endpoints, right? They're open circles. So, do we have to test them? No, because they can't equal 0. They can't equal the square root of 48. But it might be something worth considering, okay? And you'll see why in a second, okay? Because there really is no endpoint here, right? The volume, if I was to graph the possibilities for the volume, we've got open circles at either end of it, okay? All right, now we can find the derivative, okay? And I would find the derivative from here. That'll just make it easier. That's why I wanted to take the derivative right away. All right, so my derivative is going to be 12 minus 3/4 x squared. Find the critical numbers within the domain, important part. How many critical values are there? 1 in the domain, right? So there's technically there's 2, but because our domain is restricting where we can be, there's only 1. And what is it? 4. That is correct. Okay. My critical value is 4. Critical number is 4, right? Because if I plug 4 in here, and we need this whole thing to be 12, which means I need this to be 16, which means x has to equal 4. So then we take our number line and see where we're at on either side. Now I put a 0 and square root of 48 there anyway, even though those are technically not, that's where our domain is restricting us. So in between 0 and 4, positive or negative? What's the easiest number to test in here? 1, okay? So I plug 1 in here, 12 minus 3/4, that's definitely positive, okay? We go greater than 4, now it gets a little trickier. What's a good number you think in here? Well, we need to know what the square root of 48 is. How high up, is this a little less than what? 7, okay? So don't pick anything bigger than 7. What, maybe 6? 6 squared, 36. That's a 9. 36, is it negative? Yeah, negative. Okay. So what does that tell me at 4? What's happening at 4? I have a max. Are we looking for a max? We are looking for a max. That's good. Okay. Now, again, we could test the endpoints, but the endpoints aren't actually endpoints. They're open circles. So we don't need to do anything there. So I got the max. Okay, we're good. A max is going to occur at x equals 4. All right, now here's the part where you got to go back and read the question again. What are they asking me for? I did all the work. Find the dimensions. So I need both x and y. All right, we found x. Where should I go to find y? Does it matter? Can we go here? Can we go here to find y? We don't have the volume. So no, you cannot. You have to use this. And honestly, you might as well go right here. We already rearranged this one. So if I just plug this 4 in here, we should be good. Okay. Just because it's already set up with y by itself. Technically, and I teach this in Algebra 2, some of you guys remember that. I always say when you're trying to find the other one, use an original equation. We are a little more advanced now than Algebra 2. Okay, we can rearrange an equation and have confidence that we arranged it correctly. Now, if you aren't confident in your algebra, go to an original. Okay, plug 4 in for x, solve for y that way. But we couldn't have gotten this far in this be wrong. Okay, is it possible? Of course it is. But this is 48 minus 16, which is what? 32 divided by 16 is 2. So y equals 2. Okay, and here's the work. It does say answer with a complete sentence. I would get in that habit. I'm a firm believer with word problems that there's context to begin with. Think of it as you're presenting a project at your new place of work, and you want them to accept your proposal, and you want it to be nice and clean and look professional. And so that's where, to me, that final complete sentence is part of your presentation, if you will. Okay? Plus, it just makes it easier on the readers. So we've got, this is 2. Did I actually solve it? I did. 2. So we've got all our pieces now. Y equals 2, x equals 4. What are our units going to be here? Centimeters. Okay, so I've got, here are my dimensions. Dimensions to produce a maximum volume are 4 centimeters by 4 centimeters by 2 centimeters. And of course, you could write that in a little bit different way, right? It's not a it's not a hard, fast kind of thing. There's some variation there, and you could have said it however you wanted, but ultimately, that's where we wanted to go. Let's say it did ask for a minimum. Let's think about what that would be asking for, right? Because in order to be a box, the smallest possible volume box, right? On one side, since it can't ever equal 0, it would have to just be a little bit more. It would be the most shallow box in the history of boxes, right? It'd be totally wide and infinitely shallow, because at some point you measure it and go, oh, I can slice that and get a little, So I would generally say it's probably not going to happen. Okay. At the same time, if there was a spot where it potentially could be, it's not going to be down here. Could it be up here? Like, if I get we can't be above the square root of 48. But if there was going to be a minimum, because this is negative, it would have to be here. But because we're restricted, it's not possible. So yes, the answer is you can't have it. Can't have it. If we had a different domain, therefore we had different conditions for the flat piece of cardboard that we started with, maybe it would be possible. So here's where we get into an exercise that doesn't really have practical application. Well, I don't know. Maybe someone could come up with one. But it doesn't have context, I guess. It's just a regular algebra problem, you know what I mean? The word problem that just... So here's what I'm talking about. Okay, page 115. So number 2, part A asks for a maximum. And then we'll find the minimum too, because that's what part B asks for. We'll do both, but we'll do the maximum first. But again, this problem doesn't really have context. It just talking about some numbers. The sum of 2 non-negative numbers is 30. Find both numbers if the sum of twice the first plus the square of the second is a maximum. And then we'll find a minimum. So here's one where drawing a picture doesn't make any sense. There's no picture to be drawn. And so what I think you should do is establish your variables and declare what your variables are. In Algebra 2, I say it's your variable line where you declare your variables. You can pick whatever numbers you want or variables you want. I'm going to just be boring. X is the first number, Y is the second number. You know, if you want to get more creative than that, you can. And if you want to get, you know, extra specific, you could say non-negative number if you want, but you don't have to. So I need to see if there's a way to come up with two equations, because I have two variables, right? In order to solve any type of situation, whether it be optimization problems or just a regular system of equations, I need to have the same number, a minimum number of equations as I have variables, right? So since I have two variables here, I have to have at least two equations. So go ahead and write two equations if you haven't already. So hopefully you have something like this. The sum of the two non-negative numbers, x plus y is 30. And then the sum of twice the first plus the square of the second is, and there's my s I made for sum. You can pick whatever variable you want. You wrote the same thing. Everybody, who used a different, how many forgot to put a equals s kind of thing? Anybody forget something like that? Okay. So, yeah, or whatever. It doesn't matter. You can use whatever you want. But again, so this is telling us which one we need to isolate. Since I am finding both x and y, right? I'm finding both x and y in this problem. It doesn't matter whether you get x by itself or y by itself. But you're going to be focused on this equation here. This is the one you want to isolate. So actually, you go and finish it, and let's see how we turn out. Yeah. Now, what I'm going to show you is that I isolated y. But now that I think about it, it would have made more sense to isolate x, because then I would have plugged in here and I wouldn't have had to square the binomial. You definitely should, you definitely should get x by itself. Even though what you're, all right, forget it. I'm not going to do it now. I'm not going to show you my work that I did. I'm going to do.
Because I need the answer.
All right, we'll do both. Okay, let's do the hard way first. All right, yeah, the hard way first. And then we'll go back and do the easy way. That was silly. Okay, yeah, no, I definitely should have done this, and I did not do that. All right, I'm gonna do it this way. Okay, so I'm gonna plug 30 minus y in, and again, the reason why is because if I would have got y by itself, which I did in all my slides, you end up putting it in here, and then you have to square a binomial, which is not that big of a deal, but it is harder than this. Right? So I've got 60 minus 2y plus y squared equals s. I probably should put that in descending order to factor. It'll make it easier.
See, I stopped right there. I'm stuck.
No, I think this way is easier.
Do you have, is it not factorable with like integers?
Easier, Mr. Dugan.
Ooh, look at this. Yeah, wait a minute. Hold on a second. Because if we start looking at factors of 60, are there any, I mean, it's not factorable at all.
Yeah.
Did I do something wrong?
No.
Am I missing something?
Probably why you did it though.
Yeah,
But do we have to factor it if we know the domain just has to be greater than 0?
Wait, are we taking?
Good point. All right, good point. But is there a maximum value? Is there
Like a box where it can't be in the way.
We didn't.
Yeah.
right? Okay, yeah. So the maximum value is 30. So our domain. So here's the thing. Our domain, it can be 0.
Oh, well.
Okay, it can be 0.
Oh, yeah.
Okay, because it's just a number, and it can be 30. Now, we could have come up with that. Yeah, we don't need to factor anything. We could come up with this just thinking about it, right? They have to be non-negatives, all right? So we have to be greater than or equal to 0, which is why they didn't say positive. They want you to include 0 as part of the domain. Okay, and of course it can't be bigger than 30, because if it's bigger than 30, then the other number has to be negative. So yeah, we don't need to factor anything here. We're fine. Okay. I need to move this though. It's gonna move the whole thing. Isn't? Oh no, fantastic. All right, we don't have to factor that, because that would be awful. All right, so let's finish it this way. So now I'm gonna take s prime, which is 2y minus 2. So my critical value is going to be y equals 1. My number line. Now, I need to include 0 and 30 this time, though, right? Because those are endpoints. Those are actual endpoints, so we got to watch out for that. So when I plug in something bigger than 1, I get a positive. When something less than 1, I get a negative. Well, what's the problem here? This would be a min. 1's going to be a min, not a max. Okay, so here's where I still have to look at I have to look at S of 0 and I have to look at S of 30 and see where my minimum value or maximum value actually occurs.
Excuse me,
Yes.
where did you get 2y minus 2? Because it's plus 2 or? Yeah.
I took the derivative of this.
Oh.
Yep.
Okay, I see.
Okay. Yep. All right. So here's the thing. If it's 0, what's the other number? 30. Okay. So if I put 0 for x, 30. That's what 30 squared is 900. That's probably going to be the winner, right? Because if x is 30, then y squared is 0, and then that's 0. So my maximum is going to occur when s is 0. So this is my second number, right? Because I'm solving for y. Because we're talking about y's here. So second number is 30. I'm only writing this crappy because I'm going to show you my nice written version. First number is 0. Good with that?
Wait, where'd you plug in 0 and 30?
So since 0, so what we're saying, this is y, or do I have it backwards? These are y's, aren't they? These are y's. I have them backwards. Sorry. Because these values here are the y's, because we're talking about y here, right? This is all y that we're talking about. So I have them backwards. Because if y is 0, right, then x is 30, right? Because of 0 plus 30. So then this would be 60. And if y is 30 and x is 0, so we're still at 900. Okay.
Hold on, no, it's still lost.
Okay.
Like 2x equals 30, so it's.
No. So these are y's. These are y's because of this. So so these values that we're using are y's
Yeah,
because we're using this.
yeah.
Okay. So when I plug 0 in,
To where?
I'm plugging it in here
Why that one?
because that is the sum. Because if this is my y, then my x has to be 30. Because 0 plus 30 equals 30. This is first condition. If this is my y, then this has to be x. All right, so if this is my y, 30 squared is 900. And again, if this is my y, then x has to be 0. Okay? We good? Or are we still confused a little bit?
Just hold on, let me write.
Yep, it's okay. So just remember, we're talking about all this here is talking about y because of our equation, because we substituted in. All of this is y.
But like,
And so when I'm doing my comparison of the endpoints compared to my critical value, we're talking about y's. So if y is 0, x has to be 30. If y is 30, x has to be 0. And so these numbers come from this equation. And so maybe I should be more explicit with that. Okay. So here, this is, we're saying that this is y. So in this case, x would have to be 30. And in this case, x would have to be 0. Because the numbers have to add up to 30. Okay.
so then the max would be x equals 0.
Correct. So the max occurs when x equals 0 and y equals 30. Okay. Now, So when I do it, I'm going to show you the other way. We talk about x first. So we're going to determine which is the maximum x value, which we already know now. But when we go through and do it, right, this is confusing. We like to be using x all the time. And we go, this is the first number, you plug in, then there's a second number. Well, we didn't do it that way, okay, because of the algebra being easier the other way. But now, the other way, okay? So now here's getting the y by itself, okay? And so yes, we have to end up squaring this. This is, do you know the binomial squared shortcut by now? I hope you do. Square it, multiply them together, times 2, square it, okay? So this ends up being, so right, it gets a little messier, but not bad, okay? And I'm pretty sure that's not factorable either. But it doesn't matter, we don't need to factor it. We're gonna use it to find the derivative, okay? Again, we're just working the same problem from a different perspective now. The domain is still the same, okay? Now I take the derivative of s. And so now we're talking about x now instead of y, okay? So my critical value is 29, and we run into the same problem, right? I make my number line from 0 to 30 with 29 in there. When I'm bigger than 29, this is positive, and then that's negative. So again, it's still just a minimum. Still just a minimum. Okay, so it's still not going to work. So I still have to test the endpoints. And now, when I test the endpoints, okay, we are actually picking x. So if x is 0, y has to be 30. If x is 30, y has to be 0. So up with those similar numbers, because since x is 0, y has to be 30. 30 squared is 900. If x is 30, that's all 60. That means y has to be 0. We end up in the same situation. We just have them reversed because now we're talking about x. So x is 0, y is 3. That's where my max is, and then my final answer, the first number is 0, the second number is 30. All that time, that should be 900. I lost a 0. Right? Yep, that should be 900. My bad. It doesn't matter. It's gonna, when I take the derivative of it anyway, it's gonna go away. And I still can't factor it. I mean, it does matter. Obviously, if this was a free response question, I hope they'd take a point off because I had made it 90 instead of 900. I don't know.
Why would you hope to?
I don't know, because it's wrong. I made a mistake. I should get a penalty for making a mistake. You know what I'm saying. You know what I'm saying. Of course, I don't want to lose points, and I don't want you to lose points. But to me, that would be justified. You messed something up there. All right. Okay. Are you good yet or not yet?
No, because I didn't like doing that way. I solved for x, not for y, so.
Okay, we're gonna go. Yeah, we're gonna go back to that one in a second. Did you take your picture? Or do you have a question on this now?
A few different questions, but
The truth is, we could have come up with the domain without doing anything. That's what we probably should have done that. In this particular problem, we probably should have found the domain first. Just by thinking about, okay, I've got two numbers that have to be added together. They can't be negative.
Oh, okay.
Yeah. So we didn't, like in the last equation, in the last problem, we used the equation that we came up with to help us determine the domain, right? Because we wouldn't have been able to come up with the square root of 48 just thinking about it, you know what I mean? But here, since we're talking about just two numbers, we know the biggest that one could be is 30. And then that forces the other one to be 0, which is what happened here, right? In this particular problem, the way that you get a maximum result in the conditions that they give us is one of them is 0 and one of them is 30, okay? Now, the thing that's nice about about part B, finding the minimum, is we already did that. We already found it right here, okay? The minimum occurs when x equals 29, which means what's the other number? 1, because they have to add up to 30, okay? So, we can go through all that. It occurs there. You'd have to plug 29 into the original thing and show that that's less than 60, which it's not. Interesting.
But when you do like the s is 0 equals 900, what your plugs for that
is equals 59.
It is 59? Okay. Because
It's 2 times 29.
2 times 29, which is,
4 plus 1.
yeah, right, 59. It is. Okay. So, yeah, actually, we should do that. I'm going to go, let me, okay. A relative minimum occurs here. We're sure of that. But they're not asking for us. They're asking for what the minimum is, period. And since we have actual endpoints here, we have to test those too. And so by plugging 29 into this equation, and what yeah, those are x values, and I'm plugging into my sum equation here.
Okay, so like if you plug in 0 for x.
And remember now, if x is 0, that means y is 30. Right, and that's where we got the 900 from. If x is 30, then y is 0. That's where we got the 60 from. If s is 29, y is 1. So this is 58 plus 1, which is 59. So now I can establish with certainty that the minimum does in fact occur at 29 when x equals 29. Therefore, y has to be 1. Because of the minimum here, where'd it go? That here, because a minimum occurs, but we do need to test 0, I mean, we already 0 and 30. Wait a minute. No, not 0. No. Oh, yeah. We need to know what S of 29 is. Yeah, and this is 59. We already know that this is 900, and we already know that this is 60. So yes, it does actually occur there. So we do need to test those. Well, we don't need to test them. We just need to think about it. Like, we figured out S of 0 and S of 30, but we need to verify that, in fact, S of 29 is less than 60, and it is. Because if we look at 2 times 29 plus, now that forces y to be 1. That's where the 59 comes from. So yes. Now we can definitely say it is not just a local minimum, but it's a global minimum. Okay. Since there are endpoints, okay, let's go back to there it is. Since I already knew the endpoint values, we figured those out before. Those don't change, right? Or maybe I haven't flipped around. Maybe it's 900 and that was x. Do I have them flipped? I do have them flipped. It's 960. If x, we're talking about x. But either way, it's possible that the minimum occurs here, which would be odd, right? Because we just said it was 0 and 30. Now you're saying, well, 30 and 0, which this just verifies that it doesn't happen there. On the other one, we didn't have to test endpoints because we didn't have endpoints. Right? They were open circles. They were less thans, not or equal tos. And because our domain is restricted to could be 0, could be 30, we have to test those endpoints to establish that, in fact, S of 29 is the minimum, not just a local minimum.
Okay, but the part I don't get is like this plugging from S of 0. Like I can understand like analyzing numbers, which is
Yep. Where am I plugging these in?
yeah, like what are you solving for?
This homework is gonna take.
It's not going to take forever. But ultimately, that's where we've done it already. And we tested the endpoints. Okay. And if you really wanted to verify this, I'm going to go back. Okay, so there you go.